Our current understanding of the universe is based on the widely accepted Big Bang theory, which suggests that the universe originated approximately 13.8 billion years ago. However, what if our current understanding is incomplete or even incorrect? What if there is another event that caused the beginning of our universe instead of the Big Bang? Let's rewind the clock way before life on Earth, before our sun and planet were born, before stars and galaxies formed, and even before light existed. This was the era of the Big Bang, which happened 13.8 billion years ago. But what if we go further back? Many physicists say that there is no further back than that moment, because time itself started at the Big Bang. They claim that asking what happened before that moment is not a scientific question, and that we will never know what reality was like before the Big Bang, what it was made of, or why it exploded to create our universe. Such ideas are beyond human comprehension. While most scientists argue that there was no before the Big Bang, a minority of unconventional physicists have put forth a controversial theory. They propose that just before the Big Bang, all the matter and energy of the embryonic universe was compressed into an incredibly dense and finite point, which they call the seed of a new universe. This seed is believed to have been inconceivably tiny, perhaps trillions of times smaller than any particle ever observed by humans, yet it possessed the potential to give rise to every particle, galaxy, solar system, planet, and person. Some have even dubbed this particle the God particle. So how was this seed created? One idea proposed by Nikodem Poplawski of the University of New Haven is that it was forged inside a black hole, the most extreme environment in all of nature. It's worth noting that in recent decades, many theoretical physicists have embraced the concept of the multiverse, which posits that our universe is just one of an infinite number of separate universes, each a shining orb in the true night sky. That led to another intriguing idea, famously proposed by Stephen Hawking, suggests that every time a black hole is formed in our universe, it could spawn a baby universe that is only accessible to an observer who crosses the event horizon of that black hole. This leads to the question, could our universe have originated from a black hole created in a grandparent universe? Furthermore, is it possible that every time a new black hole is formed, it gives rise to a new universe? The reasoning behind these theories is fascinating. The key feature of a black hole is its event horizon, which creates a distinct boundary between the experiences of objects inside and outside of it. An object outside a black hole's event horizon will feel its gravitational pull and the curvature it creates in space, but it can still escape. If an object moves fast enough or accelerates in the right direction, it can break free of the black hole's gravitational influence and avoid falling into it. When an object passes the event horizon of a black hole, it is destined to fall into the black hole's central singularity. This is because the fabric of space-time inside a black hole is so severely curved that any infalling object will quickly reach the singularity within a matter of seconds. This process increases the mass of the black hole. From the perspective of an observer outside the event horizon, the black hole appears to grow and gain mass over time. However, this phenomenon is not limited to black holes alone. It also has implications for the entire universe. If we add up all the forms of known and measurable matter and radiation in the observable universe, including normal matter, neutrinos, dark matter, photons, and gravitational waves, we can arrive at a total sum. Our instruments can detect up to 46 billion light-years away in all directions, and using Einstein's famous equation E equals to mc squared, we can calculate the equivalent mass of the entire universe. Remarkably, if we were to compress the entire universe into a single point, it would form a black hole. What is even more remarkable is that the Schwarzschild radius, which determines the size of a black hole with the mass of all the matter in the observable universe, is almost exactly equal to the observable size of the visible universe. This incredible coincidence raises the question of whether our universe is the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. In the mid-1960s, a discovery was made that had a profound impact on our understanding of the universe. It was found that a uniform and omnidirectional radiation was emanating from all points in the sky. This radiation was found to have the same temperature in all directions, which was determined to be 2.725 Kelvin, just a few degrees above absolute zero. The radiation had a perfect black body spectrum, as though it originated from a hot thermal source, and it was found to be identical to within 1 part in 30,000, regardless of where it was observed in the sky. Originally referred to as the primeval fireball, this radiation is now known as the cosmic microwave background and provides critical evidence for the expansion and cooling of the universe, as it was hotter and denser in the past. As we look back in time, we see that the universe was smaller, more uniform, and more compact. Extrapolating further back leads to the picture of a hot Big Bang that appears to approach a singularity, which is the same condition found at the central interiors of black holes. In this location, densities, temperatures, and energies are so extreme that the laws of physics themselves break down. If we examine the equations that govern a black hole, we find something remarkable. If we start just outside the event horizon and escape to an infinite distance away from the black hole, the distance r goes from r, the Schwarzschild radius, to infinity. On the other hand, if we start just inside the event horizon and track our distance from the black hole to the central singularity, that same distance r goes from r, the Schwarzschild radius, to 0. This is significant because the properties of space outside of a black hole's event horizon from r to infinity are identical to those inside the black hole's event horizon from r to 0 at every point. This means that if we replace the distance r with its reciprocal 1 over r, or more accurately, replace all instances of r over r with r over r, the black hole's interior is mathematically identical to the black hole's exterior. It's like taking a spherical orb that's 100% reflective, a perfect mirror, and noticing that the entirety of the universe that's located outside of that sphere is now contained, albeit distorted, in the mirror image that's reflected on the sphere's surface. Over the past few decades, our comprehension of the universe has advanced significantly, leading to 2 groundbreaking discoveries that have upended the principles of cosmology. The first discovery is cosmic inflation, which suggests that the universe did not originate from a singularity, as previously thought. Instead, it was initiated by a swift and relentless state of exponential expansion that took place before the hot Big Bang. This implies that there could be a field that provides energy inherent to space itself, causing the universe to inflate. Only after the inflation ended did the hot Big Bang commence. The second discovery is dark energy, which is causing the acceleration of the universe's expansion. As space expands and becomes less dense, galaxies located far away from us begin to recede from us at an accelerating rate. Even as the expansion of space continues, there appears to be an energy that is inherent to space itself and is refusing to dilute, resulting in the universe behaving as though it has this dark energy. These 2 discoveries have caused many people to speculate about a possible connection between them. The difference in the expansion rate of the universe inferred by the 2 classes of methods used to measure it only strengthens this conjecture. One persistent explanation for reconciling the discrepancy between inflation and dark energy is the possibility of a stronger form of dark energy that existed after the end of inflation but decayed before the cosmic microwave background scattered off the primeval plasma. This suggests a potential connection between inflation, dark energy, and black holes, which could provide critical insights into the nature of this link. Black holes play a significant role in this speculation. They gain mass as material falls into them and decay through Hawking radiation, losing mass over time. The changing size of the event horizon of a black hole may impact the energy inherent in the fabric of space. It raises the question of whether cosmic inflation, which we observe as the expansion of our universe, signifies the creation of our universe from an ultramassive black hole from the perspective of an observer located inside the event horizon. Furthermore, it suggests a possible connection between dark energy and black holes. Could it be that each astrophysical black hole formed within our universe gives rise to its own baby universe within it? These speculations have been circulating for decades, attracting researchers from various fields such as black holes, thermodynamics and entropy, general relativity, and the origins and fate of the universe. While we lack a definitive or provable conclusion, there are mathematically compelling pieces of evidence that suggest a potential link between these concepts. However, to date, no physical model has been able to meet 3 crucial criteria. 1. Reproduce all the successes of the already observed phenomenon explained by the inflationary hot Big Bang model. 2. Explain or account for observed phenomena that the prevailing theory cannot. 3. Make new predictions that differ from those made by the current leading model. which can be tested experimentally. One notable attempt at achieving these criteria is Roger Penrose's conformal cyclic cosmology. CCC predicts the existence of Hawking points, or circles of unusually low temperature variations in the cosmic microwave background, setting it apart from standard cosmological models. However, despite its unique prediction, CCC and other models have yet to provide conclusive evidence or fulfill all three criteria. Unfortunately, the available data does not provide robust evidence supporting the notion that our universe originated from a black hole, or that black holes generate baby universes. While the idea holds appeal, and there are intriguing connections between black holes and the birth of universes from both physical and mathematical perspectives, it remains purely speculative due to the absence of a distinct and identifiable signature. One plausible scenario is that our universe emerged through the formation of an immensely massive black hole within a pre-existing universe. It is conceivable that every black hole in our universe has the potential to give rise to a new universe within it. Nevertheless, the crucial hurdle lies in identifying a unique signature that could unequivocally confirm or refute this hypothesis. Determining the imprint of a new idea on our observable universe, setting it apart from our current prevailing theories, presents an immense challenge for theoretical physicists. Until we successfully overcome this obstacle, these ideas will likely continue to be speculative hypotheses. We cannot definitively ascertain whether our universe was indeed created by the formation of a black hole. Nonetheless, considering the tantalizing possibilities, it would be unwise to dismiss this concept entirely. Thank you for tuning into this episode. We hope you enjoyed it. If you did, please hit the like button and share it with your friends. If you want more videos like this, don't forget to subscribe to our channel and hit the notification bell so you never miss an upload. Thank you once more, and we'll see you in the upcoming episode.